Talking about Gaussian minimum shift keying, this is a special case of the MSK, in which case a Gaussian filter converts the rectangular baseband signal to a form that is equivalent to Gaussian pulse. And here I have an image or diagram that illustrates the Gaussian pulse. This is the Gaussian pulse. So if we had a rectangular pulse that takes this shape, this is the normal bipolar and return to zero encoded pulse. But when you change it to be of the form of the Gaussian, the bandwidth requirement of this pulse reduces tremendously. So for that reason, we say that the Gaussian reduces the bandwidth requirement of the MSK signal. So this Gaussian filter is applied at the point where we have generated the bipolar non-return to zero encoded signal. We pass this signal through a Gaussian filter, and instead of now having rectangular pulses, we'll have Gaussian shaped or normal shaped Gaussian pulses that are now going to enter into our MSK modulator. And we have just discussed the MSK modulator, and as we have seen, the MSK modulator takes the form of this diagram. At this point where we are applying the Gaussian filter, and also at this point immediately after the NRZ encoder, we have our Gaussian filter. So what that happens is that we, instead of having the rectangular pulses that are generated by the NRZ, we have the Gaussian pulses that are generated by the Gaussian filter, and therefore those pulses are going to considered to be of lower bandwidth requirements compared to the rectangular pulses. So as we have seen, the use of pre-modulation of a filter with Gaussian characteristics with the MSK approach achieves the reduced bandwidth requirement. And it also gives us a uniform envelope such that the MSK by itself already have a uniform envelope. Uniform envelope is where we say that our carrier pulse, the amplitude of the carrier pulse, even if the frequency is changing, the amplitude remains relatively constant, and therefore we say that it has uniform envelope. And we also say that the spectral containment reduction of the side lobe of levels of the power spectrum and adjacent channel interference, as well as the suppression of the out of band noise. So this is a bit technical, but if we just simplify it, what we can say is that if you observe the power spectral density of an MSK signal, we have a main lobe, and these are what we refer to as the side lobes. So I've just brought in the power spectral density of the GMSK in comparison to that of MSK, and what we see in this case is that the main lobe is almost the same, but the power that is demonstrated by the GMSK with lower bandwidth bit duration product. Bandwidth bit duration product is a very significant component when we use to analyze the power spectral density of the GMSK. And what we are saying that the lower the bandwidth bit duration product, the better the power that is contained in the main lobe. So what we see is that the GMSK first and foremost demonstrates that the main lobe occupies relatively lower bandwidth requirement up to that point. And number two, the number of side lobes, these are the side lobes, the number of side lobes that are within the range of the bit rate is very reduced. In this case, we can only see 3, whereas the ones that are visible or that have significant power levels in the MSK can clearly be seen to be significant in many of them, and therefore we see that one of the biggest advantage in which the GMSK has over the MSK is that there is a spectral reduction in terms of bandwidth requirement, And number two, the power of side lobes is reduced, and therefore that significantly reduces the interference of the out-of-band noise that may arise for a given signal that we want to transmit. We have some relationship between the filter bandwidth and the bed period or the bed duration, and we say that the relationship between the pre-modulation filter, which is a Gaussian filter, bandwidth, which is considered to be the half power bandwidth or 3 dB bandwidth, and the bed period TB defines the bandwidth of the system. Therefore, if the filter bandwidth is bigger than the bit rate of the incoming binary symbols, then we say that the output signal waveform is essentially going to be equivalent to that of MSK. Whereas if the bandwidth of the or half power bandwidth of the bandpass filter or the Gaussian filter is less than that of the bit rate, then we say that the symbol interference occurs, since each data pulse overlaps the data pulse in the next position in a stable duration. So we require that for us to consider our signal to be used with MSK, the pre-modulation filter must always have higher bandwidth or half power bandwidth that is bigger than that of the bit rate. If it is less than, then we say that the indiscernible interference is likely to occur, because there's going to be overlap between the data pulses from the current one to the next one.